Chapter 4, Scatter Plots and Correlation. In chapters 1 through 3, we focused on exploring features of a single variable. In this chapter, we continue our study of exploratory data analysis, but for the purpose of examining relationships between variables, we introduce a useful graphical tool for exploring the relationship between two variables, and a numerical measure of the strength of the relationship between two variables. A medical study finds that short women are more likely to have heart attacks than women of average height, and tall women have the fewest heart attacks. An insurance group reports that heavier cars have fewer deaths per 10,000 vehicles registered than do lighter cars. These and many other statistical studies look at the relationship between two variables. Statistical relationships are overall tendencies, not ironclad rules. They allow individual exceptions. Although smokers on the average die younger than non-smokers, some people live to 90 while smoking 3 packs a day. To understand a statistical relationship between two variables, we measure both variables on the same individuals. Often, we must examine other variables as well. To conclude that shorter women have higher risk of heart attack, for example, the researchers had to eliminate the effects of other variables, such as weight and exercise habits. In this chapter and the following chapter, we study relationships between variables. One of our main themes is that the relationship between two variables can be strongly influenced by other variables that are lurking in the background. 4.1 Explanatory and Response Variables. We think that car weight helps explain accident deaths and that smoking influences life expectancy. In each of these relationships, the two variables play different roles. One explains or influences the other. Response variable, explanatory variable. A response variable measures an outcome of a study. An explanatory variable may explain or influence changes in a response variable. You will often find explanatory variables called independent variables and response variables called dependent variables. The idea behind this language is that the response variable depends on the explanatory variable. Because independent and dependent have other meanings in statistics that are unrelated to the explanatory response distinction, we prefer to avoid those words. We will sometimes refer to explanatory variables as predictor variables. The idea here is that in many applications, the explanatory response relationship is exploited to predict a response from the value of the explanatory variable. It is easiest to identify explanatory and response variables when we actually set values of one variable to see how it affects another variable. Example 4.1, Beer and blood alcohol. How does drinking beer affect the level of alcohol in our blood? The legal limit for drinking in all states is 0.08%. Student volunteers at The Ohio State University drank different numbers of cans of beer. 30 minutes later, a police officer measured their blood alcohol content. Number of beers consumed is the explanatory variable, and percentage of alcohol in the blood is the response variable. When we don't set the values of either variable but just observe both variables, there may or may not be explanatory and response variables. Whether there are depends on how we plan to use the data. Example 4.2, College debts. A college student aid officer looks at the findings of the National Student Loan Survey. She notes data on the amount of debt of recent graduates, their current income, and how stressed they feel about college debt. She isn't interested in predictions, but is simply trying to understand the situation of recent college graduates. The distinction between explanatory and response variables does not apply. A sociologist looks at the same data with an eye to using amount of debt and income, along with other variables, to explain the stress caused by college debt. Now, amount of debt and income are explanatory variables, and stress level is the response variable. Statistics in your world. After you plot your data, think. The statistician Abraham Wald worked on war problems during World War II. Wald invented some statistical methods that were military secrets until the war ended. Here is one of his simpler ideas. Asked where extra armor should be added to airplanes, Wald studied the location of enemy bullet holes in planes returning from combat. He plotted the locations on an outline of the plane. As data accumulated, most of the outline filled up. Put the armor in the few spots with no bullet holes, said Wald. That's where bullets hit the planes that didn't make it back. In many studies, the goal is to show that changes in one or more explanatory variables actually cause changes in a response variable. Other explanatory response relationships do not involve direct causation. Nations with more television sets per person have greater life expectancies, but shipping many television sets to Botswana won't cause life expectancy to increase. Even when direct causation is not present, explanatory variables can be used to predict response variables. For example, for many years, colleges have used SAT scores to predict success in college, and in 2008, Google used data on internet searches to accurately predict the spread of influenza. We doubt that internet searches caused influenza, but it is plausible that as people developed symptoms, they searched online for information about influenza. Most statistical studies examine data on more than one variable. Fortunately, statistical analysis of several variable data builds on the tools we used to examine individual variables. The principles that guide our work also remain the same. Plot your data. Look for overall patterns and deviations from those patterns. Based on what your plot shows, choose numerical summaries for some aspects of the data. Apply your knowledge. Explanatory and response variables. You have data on a large group of college students. Here are 4 pairs of variables measured on these students. For each pair, is it more reasonable to simply explore the relationship between the 2 variables, or to view one of the variables as an explanatory variable and the other as a response variable? In the latter case, which is the explanatory variable and which is the response variable? Number of times a student accessed the course website for your statistics course and grade on the final exam for the course. The explanatory variable would be number of times student accessed the course website, and grade on the final exam would be the response variable. Number of hours per week spent exercising and calories burned per week. Number of hours per week spent exercising would be the explanatory variable, and calories burned per week would be the response variable. Hours per week spent online using social media and grade point average. Simply explore the relationship between the 2 variables. Hours per week spent online using social media and IQ. Simply explore the 2 variables. Coral reefs. How sensitive to changes in water temperature are coral reefs? To find out, scientists examined data on sea surface temperatures and coral growth per year at locations in the Gulf of Mexico and the Caribbean Sea. What are the explanatory and response variables? Are they categorical or quantitative? Okay, so the explanatory variable would be the sea surface temperature, and the response variable would be the coral growth per year. And the sea surface temperature is quantitative, and the coral growth per year would also be quantitative. Predicting life expectancy. Identifying variables that can be used to predict life expectancy is important for insurance companies, economists, and policymakers. Several researchers have investigated the extent to which poverty level can be used to predict life expectancy. Name 2 other variables that could be used to predict life expectancy. Okay, so 2 other explanatory variables to predict the response variable of life expectancy would be education level and amount of exercise per week.